talk about the subject here. I want to acknowledge my co-author Violaine, who's also here at the conference. And so many of the presentations here are about the sea level contribution of Antarctica. This talk will be about how to actually calculate it from an ice sheet model. And the title of the talk is taken from our paper in 2020, where we proposed the method of how to calculate the sea level contribution from a marine ice sheet. And we were hoping that this would maybe transform into the community standard how to do these calculations. About half a year later, another paper was published that proposed another method that produces different results. And so since then, this has transformed into maybe something like a community effort to have discussions about how do we actually want to do this. And I list a couple of names here that we had intense discussions about this subject recently. So I have to report at this moment that there's currently no agreement on how to calculate the sea level contribution from marine-based ice sheet models, and in particular in the presence of bedrock changes. And recent global assessments, for instance, the results that we produced in ISMEP 6, that made it also to the IPCC report, are based on calculations with volume above flotation. I will show in a minute what that means, without any corrections. And on this figure here, you can see a comparison for a very long-term massive deglaciation experiment that Violaine has carried out with her ice sheet model. So there is a bedrock adjustment included here, albeit with a very long response time scale. So that's why we see this effect only after 40,000 years. And you see here the differences between volume above flotation on the bottom, and then the two different methods, our method and the one from Atikari et al., producing quite different results. Yeah, I want to just mention that this is for a very slowly responding Earth model, but we also see that when you have Earth models with elastic effects that have a faster response time, you can also get this relative difference between the different methods on much shorter time scale, like over the next 200 years, for instance. So I think, and maybe you agree, that this is a problem that needs to be addressed. And so it's basically, this talk is an invitation to anybody who wants to contribute to this discussion to step forward. But I want to quickly go through the issues that are at stake here and why this is a problem. So calculating the sea level contribution is difficult because we are dealing with different densities between ice, between melted water and seawater. Marine ice sheets displace seawater. Ice sheet changes cause displacement of the bedrock and of the ocean floor around it. And ice behaves like rock when frozen and like water when melted. And there's other reasons why it's complicated, as you will see. So I promised to say something about volume above flotation. This is basically traditionally how you would calculate the sea level contribution from an ice sheet model, and how I also did it in ISMEP 6. So volume above flotation is the volume of the ice that needs to be removed for grounded ice to start floating. You see this in this figure here. So this portion up here, the light gray, is the volume above flotation. Once you remove that or more, the ice column starts floating. In a floating configuration, you only have ice at flotation. Then what we do is we take this volume, we convert it into a sea level equivalent by applying a density ratio and dividing by ocean area, which we typically keep constant, in our case anyway. And then the sea level contribution would be the difference between two different configurations, or the negative sea level difference between two different configurations. For instance, moving from this to this configuration here. So there's some problems with volume above flotation that I will get to next. The first one is density, because melting ice of fresh water in salty water raises the water level. And this effect is proportional to the entire melted ice volume, so not proportional to the volume above flotation. The correction that you get from this is is more than 3%, because typically you're melting not only volume above flotation, but also volume at flotation. So depending on the ratio of these, this percentage is different. So the good news is that there's in principle agreement, at least between these two methods, about how this density correction has to be applied. And in other words, when we have no bedrock changes, our two methods completely agree. So now I have to talk about bedrock. So the problem with volume above flotation is that bedrock changes change the volume above flotation. You can see that illustrated here. In this case, we're moving from this configuration to that configuration. So the bedrock is lifted up by GIA, isostatic uplift. There's no apparent change in the sea level contribution here. But the volume above flotation increases. So if you just look at volume above flotation, this bedrock displacement here is recorded in a sea level fall because the volume above flotation increases. And you can also see that in the figure that I showed first, that even a long time after all the mass has been translated to the ocean, you see actually the volume above flotation curve going down as there's ongoing bedrock adjustment that lowers volume above flotation without any real sea level contribution. So again, there's agreement here. The agreement is that volume above flotation is not a good measure to do this when you have bedrock adjustment. The problem is that there's disagreement on how you do this calculation correctly if you don't want to use volume above flotation. So this brings me to talking about the water expulsion effect, which is basically where our methods disagree. And so again, we're moving here from one configuration to the next. In both of these cases, the ice is floating. And you may ask yourself, is there a sea level contribution in this transition? I would argue yes, because the bedrock is uplifting and it's basically displacing the water that is here. So this water has to go somewhere, and I would recognize that as a sea level contribution. But this is the debate, whether or not this should be included, because you can imagine the same configuration without the ice on top, and you basically have uplift in the open ocean, and you could argue whether or not that is an ice sheet sea level contribution or not. So the problem with this is you cannot just choose one way or the other. If you include this water expulsion effect here, you basically get to our method, which I think is somewhat consistent. But yeah, I leave it for now, the possibility that you choose one way or another. The problem is when you don't take this into account, you basically get to an inconsistent solution which is path dependent. And I think this is an interesting thing, so I want to spend 2 slides talking about this. So basically the question here is, without including water expulsion effect, so what is the sea level contribution from time 1 to time 2, or from this configuration to that configuration? So we see that here ice is floating, there's no ice above flotation, and in this configuration the same. So basically the argument is there's no sea level contribution. However, it depends on what happens here in between. So I made one case here where first there's ice melting and then the bedrock uplift happens afterwards. And yeah, from this you would conclude there's no sea level contribution except for this density effect that I described before. We can look at another configuration here where T1 and T2 look identical to the case before, but now we first do a bedrock uplift. So we're creating this volume above flotation here. And then we have the melting in the second step. So in this case, there is actually a sea level contribution because in this case here, the Attikari method would ignore that, that uplift effect here. But then you have a sea level contribution by melting this from T1.5 to 2. So that's basically the path-dependent aspect. Depending on what happens in between here, you get 2 different answers. Okay, so in our approach, we're basically avoiding that by calculating based on volume above flotation, but then applying corrections for density and for the bedrock changes that are happening. We're doing that by considering what we call changes in the potential ocean volume, as you can see here. So in case where you have floating ice, this is basically just the change in the water that is displaced by this bedrock uplift. And in the other case where there's no floating ice, then this is compensating for that volume by flotation that is created by the bedrock uplift. And so you get a kind of consistent solution that can be calculated across the entire domain. Okay, this brings me to a quick modeling example where you see these different factors here illustrated again, but I think I will just go to the conclusion, so to say. So I think the quantity that we're after here, or that I'm after anyway, is a bulk estimate of the contribution of an ice sheet to sea level change that is useful scientifically and in the policy context. We all know that local relative sea level change is the ultimate quantity that we need to inform practitioners, and this requires solving the global sea level equation. So what our perspective is really from a standalone ice sheet model, we still want to do a meaningful estimate of what that number is. And so, yeah, we have an ongoing debate about how that should be done. We also have a poster on that, number 194, so we're very happy if you want to come by and chat about this. And with this, thank you for your attention.
All right, thanks, Heiko. We do have time for one quick question. Right behind you there.
Thanks for your awesome talk. This is such an important conversation to have. I wondered if you have any thoughts on peripheral bulge subsidence. So as you have bedrock uplift, you also have a change in ocean more far field with peripheral bulge subsidence. How does that fit in?
Yeah, so in my mind, when we want to do that correctly, we would need an ice sheet modeling domain which includes that forebulging effect. And if you do include the whole area where bedrock changes are taking place, you could use this method to calculate it. And the whole idea is, of course, that you would assume that this forebulging or whatever happens in the bedrock is caused by the ice sheet, and therefore I would like to interpret that as an ice sheet contribution to sea level. But this is where the debate is. You could say, we cannot do that. Somebody else has to do that because this is not our domain. So this is basically where the separation takes place and where we have to discuss how we want to do that. Thanks.
Thanks again, Heiko. Yeah, continue these debates, these discussions over these really important issues. That's the key role of Instant, so thanks.